can't really understand it. Sort of like we know the guy yesterday in the video went to the beach and asked everyone, what's light? They're like, oh, it's color, it's aura, it's, there isn't a real good idea. We don't have a better answer than the people on the beach, really. So, write this down and star it. The wave-particle duality of light. And that means it could be either and acts like either, depending on the circumstance. So, all right, let me give you an equation that will exercise the fact that this is Einstein's equation, that it's a particle, and we're going to add it to our list. It is E equals H F. And when I look at that from a distance, I see the word elf. I know elf has an L in it, but that's how I remember this equation. The part of the H's looks like an L, so I think of elf. E equals HF is the equation that we're going to use today. And it will come off of the fact that light is a particle. Let's define what E equals HF means. E equals HF. E is energy. H is a constant. That constant changes depending on what units were used. So I'm just going to teach you one. The book does present both. If you're curious, you can read about what the other constant is. And it's called Planck's constant, after the guy who found it. And it is 4.14 times 10 to the minus 15. 4.14 times 10 to the minus 15. And just like in gravity and other places we run into constants, this is the constant that shows up in this work. And F is frequency. All right. So let's do a problem. The metal is sodium. So we have some sodium metal, S-O-D-I-U-M, sodium. And we are going to rate this metal with something called a work function. And that is the strength of the metal to hold its electrons. It doesn't want them to go flying off. So the work function is the amount of energy sodium naturally has to hold its electrons. So it's 2.28, and volts won't work because we're talking about tiny things. So we're going to use a new unit called e-volts. So you don't have to know much about e-volts, except that's what work function is used in, and it is the strength of the metal to hold its electrons. So I'll say how strong the electrons are held and I'll show you where that goes in the equation. It is going to be the E part, the energy with which the electrons are held. So 2.28 e-volts is what this metal has. We're going to shine blue light on it. So let me get some blue light. I don't know whether to make the light as a particle. I'll make it as a particle. So here comes the blue light. We know blue light, it has a lambda wavelength of 4.25 times 10 to the minus 7 meters. And we want to find the max kinetic energy of the electrons that fly off. Those are the photoelectrons. All right, you have a picture, and write down that work function of the sodium. We have blue light coming in with that wavelength, and we want to find the kinetic energy. The most of the kinetic energy can be the electrons that fly off. All right, to do this kind of problem, we start with Einstein's Elf Equation.
The energy at the light particle.
So we know what H is because it's the same in every problem. It's Planck's constant. So I'll go ahead and put in H. I know the frequency of the light, of the blue light. Oh, I don't. I know lambda of the blue light. Oh, poo. Where do I got to go to find the frequency of blue light? All right, so you've been trained to do that. So go ahead and I'll work over here in this box to find frequency. What's going to be VMM? What will V be?
3.0.
Yeah, it's always the same. Good. And lambda, we were given, luckily it's in meters, it's not in nanometers, right? Yeah, it's in meters, so we don't have to change anything. So divide that and get me the frequency, so I can put it back in Einstein's equation. We got a number. Alex, we need 3.0 times 10 to the 8 divided by 4.25 times 10 to the minus 7.
I got 7.05.
All right, so I'll say 7.1 times.
7.1 times 10 to the 14th.
Anyone confirm that?
Yeah.
All right. All right, that's in hertz, so we're happy with hertz. So that goes back over here for F. All right. Zach, this figure out the energy. The question says find the max kinetic energy. This won't be the answer, but we'll be close. Can you multiply? This is Planck's constant. This is the frequency that we just found. So Zach, put those together. And give it to me in 2 sig figs. Yeah.
Oh, that's gonna make me
It should be small.
Yeah, I have to do it for this calculator and I forgot that.
So,
2.9?
Yeah.
Anyone else? All right. It's been confirmed. So 2.9 is going to be an evolts. That is an amount of energy. And when we're talking about these things, it's a new unit. We'll only use it today, I think. So it's the unit for this kind of work. So we have, the energy is 2.9 evolts, but that is not the final answer because we want to know what's the maximum energy of the electrons that flew off. Well, no electron would fly off until this much energy entered the metal. So it took that much energy just to get the electron to leave. So we're going to have to subtract this from our evolts to see how many the actual electrons that flew off actually retained. So how many was 2.9 minus 2.28? Point what?
6.2.
All right, unfortunately we can't use the 2 because we are subtracting our significant digits. This is to the 10th column and this is to the 100th column. The least precise is the 10th column. So we can't use the 2 because it's in the 100th column. So we can end up with 0.6 evolts.
And that's the final
Alright.
answer.
Pardon? That's the final answer. All right, we'll be doing some OYOs like that tomorrow. Let me show you a little clip that will explain this thing all together at once. And how many minutes are left in the whole class?
Like 7.
You might want to stop. It's been like
How many?
15 minutes.
I'm really bad at this.
7?